Hello, Tanya Laird here, and welcome to part 2 of Lecture 15 of ENGR 231 Engineering Statics. In this portion of the lecture, I just want to work through a basic example, or actually a fairly complex example, a single fairly complex example, of finding the centroid of a compound shape. I guess previously in part 1 I referred to them as compound/composite shapes, but if I was to be really technical, I'd probably say compound shape over composite shape, but that's okay. At least in this context. Generally composites, when I think of composites, I think of things that are made of more than one material, and compound being things that have a variety of geometries kind of thrown together. So compound would probably be actually better than composite shape, but sometimes if I'm being a bit lazy with my technical language, I may mix them up a bit. But anyway, so example of centroid of compound shape. So I'm going to draw out a compound shape, and then I'm just going to find the x and y coordinates of its centroid. But it's going to be a fairly complex shape. Not something that you could solve for based on a single integral. In fact, to actually solve this, you would need to use a whole series of integrals. And we're going to do this using a tabular method like we discussed in part 1 of this lecture. So here's the, let's see, I'm going to draw out my x and y axis and describe the shape I have in mind. So first of all, we're going to have a square. I guess I could label the x-axis and the y-axis. And then we're going to have a square part of the shape. And then we're going to have a triangle. Now, let me go ahead and put some dimensions on this. So basically we have a square, a poorly drawn square at best. Does not look to scale, or I should just say not to scale, not to scale, not to scale. This is maybe 8 inches, and this is 8 inches here. So 8 inches and 8 inches. And then this triangle is, oh, let's say 6 inches. 6 inches in width. Or the length of the base is also 6 inches. Now, this would be well enough on its own, but I'm going to make things even more interesting by saying there's a hole in this thing. There is a hole in this thing, and it's going to be a semicircular hole. So it's a semicircular hole, kind of like this, with a radius of 8 inches. A poorly drawn circle at best. Oh man, that's bad even for me. Let's just say it has to have that slope there, and that slope there, and maybe we make it kind of come in better. This is not to scale, not to scale, not to scale, not to scale. And I guess if I'm going to do my dimensions in purple, I'll put purple there. So this would be 8 inches here. Then, so if this isn't very clear, what I'm looking for is the centroid of this region that I'm going to trace out in orange here. Or if I go in that direction here, I'm looking for the centroid of this region here. So basically it's made up of a square, a triangle, and then a semicircular hole. Like this here. It's a, again, a square, a triangle, and then a semicircular hole. So as we looked at in part 1 of this lecture, we'll have to subtract the area of this one. Now, I'm going to go ahead and label the pieces of this that I'll use for my subscripts as I go along. Let's see, I'm going to call the square piece 1, I'm going to call the triangle piece 2, and then I'm going to call the circular hole, or the semicircular hole, piece 3. And so again, what I'm looking for in this, maybe all this is given, and I want to find the x and y coordinates of the centroid of this composite region, or there I do it again, composite rather than compound, the x bar, y bar the coordinates of the centroid of this compound region. Of this compound region. So I want to find the x bar and y bar of this compound region. So I may have to jump back and forth a little bit here, but I'm going to start with my table here. Actually, I might just do a quick sketch of this here, maybe a very small version. So I have my square, my triangle, and my semicircle. But this one is a hole, of course, and this is 8 inches, 8 inches, not feet, but 8 inches and 6 inches. And then we're looking at this region here. And this is all in the first quadrant. So what I need to do is I'm going to create a very similar table to what I looked at last time, basically the same table. I'm going to have a P, the first column I'll just have an N, just to designate what piece number I'm talking about. So I'll have piece number 1, piece number 2, and piece number 3. And I'll go ahead and give myself plenty of space to write. Actually, I might give myself even more space. 1, 2, and 3. And then take that all the way across, and then this all the way across. Like this, then drop this down. First of all, I would want some x bar I. Or if I'm going to use n, maybe like an x bar n, or x bar n. And this would be the coordinates of the centroid of that particular piece. And then a y bar n. I might not actually want to extend these all the way down because I still have to save room for a summation space. Because some of these we're going to have to sum, as we saw before. Some of these columns we're going to have to sum. And then a y bar n. And this represents the coordinates of the centroid of each of these pieces. Now, for piece 1, that again is the square here. The coordinates of the centroid are relatively simple. It's a square. The coordinates of the centroid of a square are going to be right in the center. And so that's going to be 4 inches and 4 inches. Now, piece 2. Piece 2 is going to be a little interesting. Well, the y bar is going to be fairly simple. The y coordinate of the centroid of this piece, of this triangular piece, is just 1/3 from the base, or 8 inches. It has a height of 8 inches, or just 8/3 inches. Nothing more than just 8 inches divided by 3. But the x bar is going to be a little bit more interesting. See, the centroid of this rectangle, or sorry, not rectangle, this triangle, the x coordinate of the centroid of this, the formula for a centroid of a triangle is, again, 1/3 from the base. But that is saying that basically I know if I divide 6/3, that means from the edge of the triangle to the centroid of the triangle is 2 inches. But that's not actually the x coordinate of this. It's we have to shift it to actually get to the edge of the triangle. So this would be 8 inches plus 6 inches divided by 3. 8 inches, and that's just, that 8 inches is just to get to the edge of that triangle, and then we have an additional 1/3 of the actual width of the triangle to get to the x coordinate of the centroid of the triangle. And so that would be 2 inches, or simply 10 inches for the x bar of the triangle. And then for the semicircle here, this is one I actually need to look up a formula in a table. We could derive it if we wanted to, but when looking up a table, I find this in the I found this formula in the Hibbeler statics text, but you can find this in any number of sources. You can find the same formula in I don't know, like beer vector mechanics, or you can even find it online in Wikipedia or any number of other sources. But I always get a little antsy citing Wikipedia, but the same thing works for. But you can find the same formula in the Hibbeler text. The centroid of a semicircle, or so not a semicircle, of a quarter circle, is given by 4r over 3 pi. If you have a semicircular, I keep saying semicircular, sorry, quarter circular area, the coordinate of the centroid, if the centroid is here, if you have this here, the x bar and y bar of that particular piece is given by 4r over 3 pi. And so this whole circle would have a radius of 8. So the coordinate of the x bar and the y bar, because this is centered, because this is already positioned right at the origin, we don't need to adjust the coordinates like we did here. The coordinate of the x bar and y bar for each one is just going to be, without adjusting any kind of shifting, just 4 over 3. So 4 times 8 over 3, over 3 pi, I should say, and 4 times 8 over 3 pi, or just 32 over 3 pi. 32 over 3 pi and 32 over 3 pi. Again, that just comes from a very straightforward application of the formula, 4r over 3 pi. Then I want to get a expression for the area of each piece n. Area of n. Again, all that an, all that is the area of each individual piece. And a1, well, it's just a square, so the area of that's very simple, just 8 inches times 8 inches. Oh, and these should have units of inches. That would be just 4 times 4, or 16 square inches. And then the triangle, again, it's still a triangle, so we don't have to shift the area when we don't have to apply any kind of shift formula when calculating area. Area is just area, and the area of a triangle is just 1/2 base times height. So 1/2, 8 times 6. 1/2 of 8 is 4, so 24 square inches. Now, because this is a hole here, because this is a semicircular hole, we need to put a negative on the area of our circle. So this is going to be negative pi r squared, or equal to negative the radius again. Here, oh, I did not do well there. It is not, that's not quite right at all, is it? The area, good thing I caught that. Half of you are probably cringing there going, what the heck is she doing? That's just abundantly obviously wrong, and you are correct. The area of a square is indeed length times width, or actually length squared, and the area of that, or the length and the dimensions of each of these is 8, so that is 64 inches squared. There we go. Math be hard apparently. Okay, so negative pi r squared would then come to negative 8 squared for the circle here, or the quarter circle. And actually, I gotta back up and say the area is not negative pi over squared, it's not negative pi r squared, but negative pi r squared over 4, because we're dealing with just a quarter circle. And so then this would be negative pi times 8 squared over 4, and 8 squared is 64, so this would be negative pi over 16. Negative pi over 16. Then, if I wanted to get the, do the multiplication, and so I would have the, let's see, the an xn, or x bar n. So I need to, basically these are just going to be used to calculate the first moment of area with respect to the x-axis, well, for this one here, and the first moment of area with respect to the y-axis for this column here. And then the an y bar n. This is going to be 64 times 4. What is that going to be? 64 times 2 is 128, and then 256. And that would have units inches to the third power. And the same thing for the an y bar n. That would be 256 inches to the third power. And then here, this would be, let's see, 10 inches times 240. This would be, 10 inches times 24. This would be 240 inches to the third power. And then this here, this is basically 24 times 8 over 3, but this is basically, 24 over 3 is basically 8, so this would come to 64 inches to the third power. 64 inches to the third power. And then let's see, this would be, well, this would be all sorts of fun. 32 over 3 pi times negative pi over 16. So first the pi cancels out, and then that goes away, and that becomes 2. So that would just be, if I'm mathing this correctly, negative 2/3. Just simply negative 2/3. Does that make sense? Let me double check that. Oh, not at all. Oh boy. making all sorts of math errors tonight. This is probably why I shouldn't record lectures at 1 in the morning, but that's another thing entirely. This is negative 16 pi. Negative 16 pi. There we go. I was within an order or two of magnitude. What's an order of magnitude among friends? So, famous last words. Negative 16 pi. That one's bad even for me. Times 32 divided by 3 pi. 32 divided by 3 pi. So the pi and the pi will cancel out, leaving me with 16 times 32 divided by 3. And that comes to, let's see. So negative 16 times 32 over 3. It's probably not going to be an exact, but no, that'll be negative 16 times 32. And that comes to negative 512 divided by 3. Negative 512 over 3 and inches to the third power. Negative 512 over 3 inches to the third power. Again, just multiplying the expression for the area, negative 16 pi, times the x-coordinate here, 32 over 3 pi. And the y bar, the an y bar n would be exactly the same, negative 512 over 3 inches to the third power. And then we would simply need to sum each of these up. And let's see, I might just do this as an ugly decimal because I don't think this is going to come to any kind of nice even number. So 64 plus 24 minus 16 pi. So 64 plus 24 minus 16 times pi. This comes to 37.73 inches squared. That is the combined area of the entire shape. Again, considering the reduction in area from the quarter circle hole. 37.73 inches squared. Then each of these will have different results this time. So 256 for this column plus 240 minus 512 divided by 3. And this comes to 325.33 inches to the third power. And again, this is going to be your an x bar n, or the summation of that, or the qx, or sorry, the qy, the first moment of area with respect to the y-axis. And then the summation of this, 256 plus 64 minus 512 over 3, and this comes to 149.33. Again, inches to the third power, and what this represents is this is simply the an y bar n, of course, in the summation of this. This is qx, the first moment of area with respect to the x-axis. So this number here is the total area of the shape. This area here represents how much area you have how far from the y-axis, and this number here, I shouldn't say area, this number here represents how much area you have how far from the y-axis, and this number here represents how much area you have how far from the x-axis. And then finally, x bar, the combined x-coordinate of the centroid, is going to be just qy divided by a, which is this divided by this, 325.33, divided by 37.73, inches to the third divided by inches squared. And if I throw that in my calculator, this comes to an x bar of 8.62 inches. Which looks about right, assuming I didn't make any kind of math error, which is certainly possible. We did have a few errors along the way, and hopefully we didn't miss any, but it's always possible. Y bar then is going to be equal to the first moment of area with respect to the x-axis divided by the overall area of the shape. And so that's going to equal 149.33 divided by the same area of 37.33, and this would have units of inches to the third power, and this would have units of just inches squared. Dividing those out, I get an overall area, an overall y bar of 3.96 inches squared. not sorry, inches squared, just inches. 3.96 actually, inches, just inches. So my x bar, y bar, the combined centroid of this compound shape is 8.62 inches, comma 3.96 inches. And this represents the overall average location of the area of the shape. If it was, for example, if it was, now what does that mean? Of course, well, if this were a simple, for example, if this were a flat plate, that would actually represent the location of the center of mass. But for a plane shape, we can have for a plane shape here, an area, you can have a centroid independent of center of mass. But for now, just accept that what we're looking for is this location of the centroid, and the location of the centroid of this compound shape would be at 8.62 inches, comma 3.96 inches. Again, assuming we didn't make any math errors, which is, of course, as you have seen in this lecture series, certainly possible. But regardless of whether I made any math errors or not, I do believe that is correct. But regardless, the method is correct. So if you notice any math errors, I would encourage you to work through this and check my numbers and etc. But if there are any math errors, please let me know, and I'll note it in the comments. I'll double check it and note it in the comments. But regardless, please let me know if you have any questions on how this worked. All right, so I think that'll do it for lecture 15. I think for lecture 15 was going to be relatively short, just covering two aspects of part one covering the theory of the centroids of compound shapes, part two covering a brief example working through these, and really that's what I wanted to cover in lecture 15. In lecture 16, which I'll be posting later, well, not tonight, but tomorrow or such, we'll be looking at moments of inertia, beginning to look at moments of inertia and their application to bending moment capacity. But for now, I think that'll do it. Please let me know if you have any questions. Hopefully you found this a little interesting, or if not interesting, at least illuminating a bit, or educational at the very least, or at the very least, hopefully didn't put you to sleep too quickly. So please let me know if you have any questions. If not, I will see you soon for lecture 16 of ENGR 231 Engineering Statics. Again, please let me know if you have any questions. I will see you soon for lecture 16. And as always, thank you.